Great, well, thanks very much for the introduction, and of course thank you to the organisers for allowing me to speak at a wonderful three-dimensional workshop. So as advertised, I'm going to talk today about average ranks of elliptic curves after p-extension. This talk sort of breaks into three parts. So first I'll give the necessary background so that we can actually see what the problems are that I'm going to talk about. And then the second section, by far the largest, I'm going to talk about the main tool that I use to get a hold of average ranks, which is studying the failure of Galois descent, in this case for p-Selmer groups of elliptic curves. And then after a lengthy build-up, we'll actually talk about what I can tell you about average ranks. Okay, so that's where we're going today. So, without further ado, if I'm going to tell you about average behavior of arithmetic objects, I'm going to need to give you a parameterization of them. So for us today, the set epsilon will be a set of Weierstrass equations, EAB. So these are the form y squared equals x cubed plus, ax plus b, where here a and b will be integers. They'll satisfy a discriminant non-vanishing condition. So 4a cubed plus 27b squared can't be 0. So at this point we have a collection of smooth cubics, elliptic curves. And then finally we'll require that the greatest common divisor of a cubed and b squared, it needs to be 12th power free. Trying to fit a set bracket on the end of that. So this last condition may seem a little opaque if you haven't thought about average questions for elliptic curves before. Its purpose is simply that if you already have some choice of elliptic curve over the rational numbers in mind, and of course you only care about the curve, you don't care about how I presented it, so up to isomorphism, then this final condition on the greatest common divisor ensures that there will be exactly one curve given by the equations in epsilon, which is isomorphic to the one that you actually chose. So this gives us a concrete way to talk about all elliptic curves over the rational numbers. And I guess I probably don't need to repeat this, but I do need the notation. So we have the theorem of Mordell and Weil, which for our curves of interest today says that for one such and then a number field k, the set of k points is of course a finitely generated abelian group. So you have some infinite rank component here and then some torsion subgroup. And of course, as the title suggests, today the main sort of questions will be, what can we say about the typical behavior of this integer here, the rank? And I guess a sort of informal question is, how large should this be? If I start drawing my elliptic curves randomly out of a bag, am I expecting this rank to be 10 trillion or somewhere around 1 or 2? Just while this is on the board, I should say the torsion subgroup here, at least from the statistical perspective, it's boring. It doesn't exist. So 100% of the time, this is trivial. So somehow, at least from the perspective of E of k being a group, the rank is the only data that is of any statistical interest, at least in this family. Okay. So now what I'm going to need an ordering with the Northcott property. So definition. For each positive real number x, epsilon of x is going to be all of the elements in epsilon satisfying some height bound. So a cubed and b squared are bounded in absolute value by our x. So now I have a genuine finite set. I can actually give you a notion of average. So our notation today, for each number field k, the average rank of k points in the family of elliptic curves defined over the rational numbers is just, you take the naive average inside of these finite sets of the thing in question, the rank. And then we let x grow very large. And since we want to know sort of how big is it, we'll take a lim sup. And of course, the reason I have to take a lim sup and not a limit is because there is no number field that we can put here for which we even know that the limit exists. Yeah, it's a bit of a depressing state of affairs there. Okay, so I guess I'll leave the schedule up for a little bit in case people arrive late. Okay, so this talk is about average ranks after p-extension. So I should say something about before p-extension. So what was known before the theorems I'll give today sort of boils down to some work of Bhargava and Shankar from 2010. And maybe I'm betraying their results a little bit by writing it like this, but in our language, what they show is that the average rank of q points on these curves is finite. They give an upper bound for it. I'm not going to write it down because my ordering is ever so slightly different to theirs, and you don't want hideous numbers on this board. So for our purposes, what they show is that it's finite. This doesn't tend off to infinity. Somehow, ranks are well behaved statistically. So this then prompts some questions for general number fields, I think. So I guess the first, most obvious question from this is the same true if I just replace q with k? So for every k, is the average rank of k points still finite? Or is there some number field k that starts to, I don't know, it has some really intrinsic connection to elliptic curves. It forces lots of them to have lots of rank points. For example, if you sort of look up here, the equation, if I take lots and lots of quadratic extensions, somehow I can put in any x I want, and then I take a square root, and I can force a y point. So somehow we can see that taking lots and lots of quadratic extensions will force more points onto our curves, but lots requires I take infinitely many, right? And so we really just want to answer the number field question here. So it doesn't seem unreasonable to expect this, I don't think. And then if this is true, well, we can then ask, how does it depend on k? So how, does it depend? And I guess this first question is quite precise, the second is quite vague, so to give two slightly more concrete interpretations of this, if I just take k to have some fixed structure, so say I want k to just be, I pick a group and I want a G extension. So some Galois extension of the real of the rational numbers, not the reals, with Galois group G. Then of course, for a fixed elliptic curve, of course it cares which k I chose. But as I average over all of the elliptic curves, does the family really care which one? Or is there some kind of smoothing going on where the elliptic curves typically only care about which g I chose, or just the degree, or some other not determining data of the number field? Another way that you could interpret this sort of dependence is, what if I take a tower of number fields? So I have k0, k1, and so on, and I reach some infinite extension up here, k infinity. And moreover, say I know in advance that some, all, a quantity of elliptic curves have rank that grows towards infinity. So for example, k infinity could be the algebraic closure. We could approach that as quickly as we like. Certainly the rank tends to infinity as we approach that. Then I guess it's not clear how fast that should happen. So how fast, on average, does this rank tend to infinity? What does growth of ranks look like in this whole family? Okay, so hopefully those questions are precise enough for you to keep in mind. From here, I guess, I should start telling you what tools I need to actually access ranks. Oh. So Mordell Weil groups, these groups of k-rational points, wherever I've written them, they're quite bashful. They don't like to tell us very much about them. The rank is, of course, the subject of debate, conjecture, and, well, every kind of uncertainty, really. So instead of asking the Mordell Weil group, we ask a much more accessible group. So for each prime number p, each element that we're interested in, each curve, and then each number field k, we have the p-Selmer group. So this thing here. And its miraculous relationship is that it contains the set of k points modulo p. If the p-Selmer group is unfamiliar, the only thing that really you need to know about it is that it's an FP vector space. And, rather key, I guess, at least in principle, it's computable, which compared with the rank is a rather nice property indeed to have. And of course, every copy of the integers that appears inside E of k, well, is going to contribute a z mod p here. And so this gives you this inequality that the rank of E over k, oh, I've made this difficult for myself. It's at worst, sorry for the slant, the dimension over fp of this p-Selmer group. And this inequality is rather fundamental to understanding average ranks at the moment. Somehow, the fashion is to understand the dimension of the p-Selmer group instead, and that in turn tells you something about the rank. And indeed, this is where this theorem of Bhargava and Shankar from 2010 comes from. So the sort of main results that they prove in this direction, again, maybe I'll betray them a little bit, is that for now, a very small set of prime numbers, 2, 3, and 5, we know that, well, this is in Bhargava and Shankar, we know that the average dimension, so again, average taken in E of x, of the p-Selmer group of E over the rational numbers is finite. Again here, so. Actually, what they do is they compute the average size of this group, and in turn that tells you something about the dimension, but this is really the useful thing if you want to talk about ranks. So bear this particular condition in mind because it will show up later on, that p can only be 2, 3, or 5. Okay. I guess, yeah, at this point, I probably want to just take a new board, so. Ugh. Okay, so when Bhargava and Shankar are proving this result, really what they're understanding is all of the information that we could ask about this p-Selmer group, right? I've only told you that it's an FP vector space, and so the sort of fundamental data that we can ask about it is its dimension or its size. But in our setting, we were talking about average ranks over extension fields, so we could potentially have a little bit more structure to play with. I should probably write both. So, actually, I'll erase this and then I'll tell you what I'm going to say about that. So yeah, because we're going to have extension fields, there's a natural action of Galois groups that could be present here. So say, put this in the other color. So say K is now a Galois extension of some F, and G the Galois group. Then, of course, there's the ambient action of the group on the K points, right? You can just act coordinate-wise, and this descends mod P. And conveniently, since this is some cohomological construction, there's a group action here as well, which is preserved under this inclusion. So in particular, we're not just studying a vector space anymore. This is an FPG module. So what we can hope to do is leverage this group action to tell us more about the Mordell Weil group. So in this direction, I guess we had Adam's talk yesterday where he was asking about how the group acts on E of K when K is quadratic, but he was varying the field, not the curve. So this is somehow dual to that kind of question. So hopefully these are dry enough now. Okay, so what can we ask about G actions? Well, I guess the most general question available to us, so that we don't have to restrict the group or the prime, is, well, what does the fixed space look like? Right, there's always a fixed space. And of course, look like is a bit vague, so let's say, what is its dimension? 2 on average. Oh, good point. Yeah, that would be really trivial, wouldn't it? Thank you. The G should be on the outside. So looking at our notation, and since I put G in the right place, I guess where I wrote it would suggest that there's something that we can maybe hope for. So is the Galois fixed space in here, and I just put G back inside, is this just the same as the one over this lower field, F? Right, certainly, at least for me, naively, I just want to be able to take that G inside and make everything work. And the answer to this question comes in 2 distinct flavors, not vanilla and chocolate, but yes and no. So FP does not divide the degree of the extension, the order of this group, so that somehow, at least from the perspective of group representation theory, your representation is nice. Then in this case, absolutely. These 2 things work out the same. Sort of to say in words, you kind of look at the Weil restriction and it has an isogeny to some product of twists, and that isogeny is of degree coprime to P. And so you end up with a decomposition going on here. The other flavor, when P does divide the order of the group, no was a bit of an unfair characterization. It could happen, but I guess not always is the most precise thing I can tell you there. So not always is maybe a bit unsatisfying, right? I need to give an example to explain to you what that could mean. So, put that a bit high. I'm going to need 2 boards for a big example. Annoying. It's not going to be dry, is it? Okay. So I want P to divide the order of the group. guess I should take p as small as possible. So let's take p equals 2. F, let's make that as easy as possible. Put it on the rational numbers. And since p has to divide the order of the group, let's make k a quadratic field. And of course, G is then cyclic of order 2. And for the purposes of this example, instead of looking at all elliptic curves, let's look at a specific family. So the congruent number curves, which are given by equations ED, dy squared, which x cubed minus x, where here d is a square-free integer. And the thing we're trying to work out is how similar are these two groups. So maybe I'll write this here. What is the difference between the dimension of the 2-Selmer group of a congruent number curve over the rational numbers, put the other one over here, and the dimension of the fixed space in the 2-Selmer group of a congruent number curve over K. So we want to understand how different these two things can be. Well, for congruent number curves, we can actually give an answer. So on the left-hand side, the congruent number curves, 2-Selmer groups over Q, I guess one of the oldest results for statistics of Selmer groups is due to Heath-Brown from about 1994. And what Heath-Brown proves is for every integer r, he finds explicit alpha r such that the probability, I'll maybe be precise about that in a second, that the dimension of the 2-Selmer group of a congruent number curve over Q is r is exactly this explicit constant alpha r. So probability here, I just mean you take d up to some bound, satisfying the condition, and then let the bound tend to infinity. So I'm not going to tell you what these alpha r are. If you think back to Adam's talk, there are these products of powers of 2, and that's kind of what happens here, but I try to spare you as many ugly expressions as I can on the board. The takeaway is not only is there an actual non-zero probability for all r at least 2, but sort of takeaway numerically is that the probability that this dimension over Q is at most 6, which I'm sure we can all agree is a very small integer, is more than 99.9%. So it is extremely likely that the thing on the left is very, very small. So what about the right-hand side? Does that behave similarly? As long as r is at least 2. The elliptic curve has full 2 torsion, and so you can't possibly have the dimension being smaller than 2 because each 2 torsion point is contributing to the dimension.
Maybe you could repeat the question for the people in the other room.
Oh, sorry, yes, sorry. Yeah, the question was, these alpha r, are they non-zero? And yes, was my answer, as long as r is at least 2. Sorry, is that okay? Okay, so the right-hand side, what happens here? Well, this was something old. Here's something quite new. So it's a theorem due to Adam Morgan and myself from the end of last year. I don't have anything borrowed in blue, by the way. So if we take beta of d to be, you take the dimension of this fixed space, take off log d, LL being log here, divide by some kind of standard variance. So in this case, it's 2 log d. Then this function beta is normally distributed. With mean 0, variance 1. This being in the sense of the Irish-Katz theorem. And so again, you take all d up to some bound, and then you let that bound tend to infinity, and these probabilities approach that of a normal distribution. So this behavior on the right-hand side is really substantially different from this on the left. I mean, since this function has mean 0, the dimension of this fixed space should be roughly around log d. And so, sort of comparing to the takeaway here, if I take z to be the largest real number you've ever seen written on a blackboard, and I ask, what's the probability that the p-Selmer group fixed space here is at least at z, then that's always going to be 100%. So these two things are usually, at least in the family of congruent number curves, extremely different. And this difference, I guess, you can think of being roughly around log b. That doesn't give us much hope for using Selmer groups over the lower field to understand the fixed space in the Selmer group over the higher field. I should probably say, just while it's up there, this kind of behavior is not unique to congruent number curves. You can take any quadratic twist family of an elliptic curve with full 2 torsion and no cyclic 4 isogeny, and Heath-Brown's result would be replaced with a similar one due to Swinnerton-Dyer and Kane. I think Alexander Smith has some results for other kinds of elliptic curves. Okay, so this whole board, I was stuffing a rabbit into a hat in front of you, because in fact, now if we talk not about congruent number curves and quadratic twist families, but we talk about all elliptic curves, then this growth behavior actually ends up being smoothed out. So the main theorem that kind of underpins today's talk for about June-ish this year is for every prime number p, every Galois extension k over f of number fields, finite Galois, writing again G as the Galois group. Then this difference between the fixed space and the Selmer group over the lower field, if we take an average in this family, then this is actually bounded. And moreover, there's some constant here in your head, take it to be somewhere around 50. You get the number of ramified primes in K, so this is the prime counting function in the discriminant, times the degree of F. So that's really all that's contributing to this failure. So in particular, if I want to ask statistical questions about this fixed space over here, then I can reduce to understanding the fixed space over F if I throw in this extra nonsense here. So I want to give a very quick overview of the ideas that go into the proof of this. I think they're quite nice. Tate-Shaffer-Evich group. In fact,
Can you repeat the question again?
oh, sorry. So Dan's asking, this growth in the p-Selmer group on the right-hand side, do we expect this to be coming from SHA or from points on the curve? In fact, in our paper, we show that this growth is coming from SHA. To say roughly, I mean, the rank of E over K, well, since K is fixed, you have it being the sum of the rank of E over Q, and then the rank of E twisted by K over Q. Both of those being understood by Heath Brown or Swinnerton, Dyer, and Kane's results on the left to be sort of well-behaved. And if you interpret the well-behavedness correctly, then that tells you that the rank has sort of similar bounds to the 1 over Q. And so this growth has to come from SHA. Yeah, I think actually, maybe I should say now, since you've asked, this kind of bound here, I actually think this number of ramified primes thing here is coming explicitly from SHA. And I'm currently writing up a proof that kind of morally shows that in the case that K is quadratic. So somehow SHA over extension fields, I guess it does become larger, and there's something that's really, really forcing that. Okay, so what goes into the proof? Well, I guess if I just take this difference, and I'm on my iPad and just lift it over here for a moment, and then the first thing that we do is you want to bound this using some, well, I guess some input from duality. So here, I mean, Poitou-Tate duality, so it's the Wiles-Greenberg formula that we're using. You can bound this by a sort of a purely local behavior. It's a sum of these functions IL of E over K, where this thing depends only on the structure of E over the completion. Oh, I should say, I'm simplifying to F equals Q here to spare some notation. So we're summing over primes, and we have these local constants that are coming from the behavior of E over QL, and then whatever K's completion is. And then the second input is that if L is unramified, then what's the nice way to write this? The probability in this family that IL for this fixed L of E over K is non-zero. This is roughly of order L to the minus 2. The 2 being the very important part here, because we're going to sum over all prime numbers. And I think there's one more ingredient that I need to tell you. Yes. And most usefully, this IL of E over K is uniformly bounded in L and E. So in this case, it's at worst 8. So then, when we start taking averages, you're going to sum over all your curves, and then over all primes, these constants. You perform the analytic number theory trick, you swap them around. So now you're summing over all primes. Well, the ones that divide the discriminant, we don't know very much about, except that it's at worst 8. So pop an 8 there, I guess. Yes, so this, yeah, what's the least hideous way to write this? So IL of E over K is the dimension over FP of, okay, so you take the QL points, is that right? Yes, the QL points on E, modulo norms from the completion at k of kv points plus p times the ql points. Yes, so what's really going on behind this inequality is I'm constructing some sort of some Selmer structures in cohomology, so I'm imposing everywhere local conditions on H1, and that in turn allows me to leverage some duality to use the Wiles-Greenberg formula essentially to get this kind of everywhere local sum that comes out. Oh, sorry, the question was, these things here, are they coming from some kind of cohomology? Is that right? Okay. Yes, so this thing, you're sort of picking up some information at the ramified primes, and then something of order sum over all primes L to the minus 2, which is, of course, constant. How long do I have left? Oh, only 5 minutes, gosh. Okay. Oh, you're right, I started at 1/4 past, thank you. Thank goodness I'm running out of time. Yeah, so roughly speaking, you're picking up, in this case, just the number of ramified primes, because I chose F to be Q. And sort of, yeah, the extra information is coming when F is not the rational numbers, it's just coming from having sort of more places, each one above each L sort of thing. Okay, so I started off this talk, and I sort of suckered you all into the room by saying I was going to talk about average ranks. I've just wittered on about fixed spaces in p-Selmer groups for a while. So now I should really bring us back around and talk about what this actually tells us for average ranks. Okay. Take this extra board on the right. I hope everyone's seen the schedule change. Ah. Okay, so what does Galois descent have to do with Selmer groups? Well, everything, but what does it have to do with ranks? So I guess I'll just plant the theorem on the board, and then I'll talk about why it's related. So our base field F, it can be either the rational numbers or a multi-quadratic field. So by this, I of course mean you can have finitely many square roots of rational numbers. P, I asked you to remember a condition on primes. It can be 2, 3, or 5. And then finally, the main player in the story, K has to be a Galois P extension. Of F. And so by this, I mean not only that it's a finite Galois extension, but the Galois group has to be a P group. And in this case, with all of this technology set up in front of us, In fact, the average rank of k points on elliptic curves is bounded. It is finite. And again, I'm hiding a constant. In your head, you can think 50. This is at worst the number of ramified primes in k times the degree of k over the rational numbers. There is, of course, I want to point out, over here I had f, so there is a slight difference in these bounds. So these conditions are all a little bit mysterious. I should probably give just a couple of examples. Of course, this theorem applies to k could be an S3 extension. It could be a quaternionic extension. It could be abelian. It could be Z mod 5 to the 10 trillion. Oh, maybe not 10 trillion. I can't write that many zeros. There's plenty of extensions that fit into this family. So where did the conditions come from? I didn't have any conditions on my Galois descent. Well, here's an idea of the proof. So I said that the sort of motivating thing for Selmer groups was that we could bound the average rank by the average dimension. So I'll just write avg dimension of the p-Selmer group. And on this left-hand side, I'll keep track of what my notation means. So at the moment, p starts off as any old prime number, k over f, any Galois extension of number fields. And I've forgotten to say finite again. And of course, G will be the Galois group. And so far in this generality, of course, this bound holds. Now, the first restriction we're going to make, if G is a P group, so we have a Galois P extension, then the dimension of this whole FPG module, just this fact just essentially comes from representation theory. And this is at worst now the average dimension of the hero of our story from earlier. So the fixed space inside this p-Selmer group times the order of the group. Of course, it's not at most that, because that would be, well, that would just mean everything was trivial all the time. Okay, so next, we want to feed in our Galois descent theorem, because that tells us I can reduce down to a smaller field. So that's what I do. So now this is at worst the average dimension over FP of the p-Selmer group, now over my field F, which so far has no restrictions. Again, the order of the group, but I have to add on this extra error, omega delta k times the degree of F. And that should be a less now, because there's some weird constant nonsense. So this is where we now have to make another restriction. Because now that we're just taking average dimensions of these p-Selmer groups, we need to appeal to the literature to see what we can actually do. So the first constraint, let's take f over q to be, I wanted to say q or, but at worst multi-quadratic. So it can be the rational numbers or a multi-quadratic field. And in particular, the elliptic curve over f, well, this kind of starts to look a lot like the product of some quadratic twists of elliptic curves. So we can reduce understanding the dimension of the p-Selmer group over f, reduces to understanding now the average dimension of just these individual quadratic twists, so the p-Selmer groups of elliptic curves over Q, but you pick up sort of the number of quadratic twists you're dealing with, which just happens to be the degree of f over Q. And again, we multiplied by the order of the group, but that's just the degree of k over f, so I can just replace this. Okay. Again, still have this extra stuff coming from the Galois descent theorem. Okay. And then finally, now I've reduced down, I'm just talking about p-Selmer groups over Q. And that's why I asked you to remember Bhargava and Shankar's result back at the start. Because we understand p-Selmer groups over the rational numbers for exactly p in 2, 3, 5. You get a worst degree plus this factor. So that's where these weird constraints come in this theorem. Really, we're just leveraging some representation theory and then trying to reduce down to the Bhargava-Shankar theorem. After, of course, we filter in this result here. So with 10 minutes left, I didn't just ask, is the average rank finite? I wanted to say something about its behavior. So I'm going to give a couple of examples of what this theorem means for the behavior of average ranks. So at the start, I gave, well, I've rubbed it off now, I guess, but I gave two interpretations of what I meant by behavior as we vary this field K. So the first, I said, what if we fix some structure for K, and then we ask, how much on average do elliptic curves care beyond that fixed structure? So for the first example, let's look at some S3 number fields. So let's take a specific family of them. So for each prime number L, let's take KL will be, you take the rational numbers, cube root of L, and then you take the Galois closure. So this is my attempt at writing a zeta 3. Primitive third root of unity. Then all of these, by Kummer theory, are cyclic degree 3 extensions of Q zeta 3, which in turn is a quadratic extension of the rational numbers. Galois 3 extension, quadratic field, great. My theorem applies. And what it says that the average rank of KL points on elliptic curves, well, it's at worst, well, there's a constant here. I didn't tell you it, but I'm going to use it in a moment. Then there's the number of ramified primes. But the only things that ramify are, of course, 3 here and L here, so that's at worst 2. And to the degree, well, that's constant for all of these, that's just 6. So I get a uniform bound for the average ranks over all of these fields. And it just so happens that the best I can do at the moment, 70.68. Explicit constant, not small constant. So I guess in the sense of Martin Widmer's talk yesterday, this average rank function certainly doesn't have any Northcott property. Infinitely many that will satisfy the bound 70.68. So I guess if you woke up this morning wanting to count S3 number fields and you wanted to count them by average rank, then I've disappointed you a little bit. But you probably didn't wake up wanting to do that, hopefully. So that's what happens if we fix some structure. Somehow the ramification is really all that matters, and the degree. So if we then talk about the other interpretation, towers of number fields, then we want to understand the average growth of the rank. So the tower I'm going to talk about today, so first, let F be an imaginary quadratic field. And F infinity over F, that will be the anticyclotomic ZP extension. So just to sort of mention briefly what I mean here, you have F infinity. Down here you have F over Q, degree 2 extension. And since the Galois group here is the p-adic integers, you have all of these intermediate fn's given by p to the n zp, which in turn give you cyclic extensions. And this anticyclotomic is really just saying that Fn over Q has to be dihedral. That's all that's going on extra here. Now the reason that I've chosen these is because some conjectures of Maser suggest that for infinitely many of the curves that we actually care about, so these elliptic curves over the rational numbers, the rank of E over each of these intermediate fields, so as we approach this limit point at the top, is roughly p to the n plus some constant, which depends on E and F, but really what I want you to sort of pick up from this is that we're seeing growth of ranks the whole way up the tower, and somehow it looks a bit like p to the n, which is the degree of this extension here. So if we compare this to the statistical theorem, then, well, I have the average rank of Fn points on all elliptic curves, not just on these infinitely many. It's growing at worst. Well, there's the ramification again, but in a ZP extension, the only things that can ramify here are the primes above P. And of course, then you have whatever did so before you got to F, but that's uniform if I just fix the field F, right? I'm going up this tower, it doesn't matter what my F was, or at least my Fn all will already see the F. So the ramification is at worst, what, 2 plus something depending on F, and then you have the degree, which is e to the n. So somehow comparing to these conjectures of Maser, on average, this is kind of the worst behavior that you're expecting for ranks. You shouldn't see growth much stronger than this. Okay, so those are my two examples for what this means for behavior. I just want to say one more thing I forgot to say a moment ago. So this P in 235 thing, it's the only step in this proof which isn't a limitation of the method, but is a limitation of like our knowledge today. So if you're willing to assume some conjectures, I guess due to Poonen and Rains, then in fact, this step should hold for every prime number P. So somehow we can ignore that if we're willing to assume that what we believe to be true will actually hold in the end. Whereas all these other steps in the proof, they were actually sort of fundamental to what I was doing, right? I had to be able to bound by the fixed space. That does require a P group. You can't do that for non-P groups. And the multi-quadratic thing was really using that elliptic curves over F look like sums of quadratic twists, which again won't happen if I've not got a multi-quadratic field. Okay, so I guess that's everything I would like to tell you all today. Thank you very much for your attention.
Thank you very much for a very clear talk. Are there questions? Can you repeat the question first?
So the question was, if we assume the BSD conjecture, then does it sort of change how these averages behave? Is that right? So I don't, to make sure I don't say anything completely false here, I don't think that BSD should tell us anything. Although in saying that, yeah, one interesting thing actually, that's a very good question, thank you. One interesting thing might be to work out, if you look at the constant in the BSD conjecture over K, then is that telling you something? Yeah, is that somehow what's causing this growth of SHA, which I think is from, was it Dan that asked the growth of SHA? So I said that sort of the largeness of this bound that's coming from the ramification is coming, I think, from SHA. Maybe if you look at the BSD constant, then that can tell you a little bit more about that. Yeah, thanks for that. That's a very good question. I'll have to think about that.
Any other very good questions?
I guess it depends on what you mean by input that. So Bhargava, well, yeah. But I guess, so the Poon and Rains, thanks, this is a great question. I should repeat it. Thank you. I just remembered. So the question was, these models of Poon and Rains, they use, well, they kind of suggest how p-Selmer groups behave, and so if we input it in here, does that tell us some more about this limit, right? So the models of Poon and Rains, what they do is they sort of, well, it is a fact that, do I have p-Selmer over Q written somewhere? No. So it's a fact that the p-Selmer group over the rational numbers is somehow an intersection of maximum isotropic subspaces. And Poon and Rains' model is essentially saying that's all the structure that we should care about statistically. And so, we should expect a random intersection of maximized isotropic subspaces to be exactly what the p-Selmer group looks like. But now that you're looking over our higher fields, there's more information at stake, right? There's this Galois action. So it's one thing that I have thought about and continuously think about is how should one think about sort of a random group action on intersections of maximized isotropic subspaces. So somehow, yeah, I don't think it would make sense to just put Poon and Rains' model into this difference because there's just more structure there in front of us that we would need to understand. But certainly I think you could build a model out of Poon and Rains', and I have given that some thought. Thank you.